Okay, so now we will talk about how do you use these nonparametric regression models in practice, and we'll talk about three different use cases: description and prediction, and for causal inference, like we've been doing for our other regression methods. The first one is for description. So if you just want to describe a relationship. Okay, we did regression trees, so you've seen actually that some nonparametric methods are actually very interpretable. So let's say you fit a depth 4 regression tree on, if you're predicting, let's say, mortality rates for people with a particular disease, and your predictors are age and income and whether they have insurance. If you're fitting this regression tree, the predictions, it's very interpretable actually to say, okay, why did this person get such a high predicted risk or whatever? Well, it was because their income is less than 100,000 and they're older than 40 years old or whatever. So it can be very, very interpretable. I think actually this is way more clear than logistic regression, where you're saying something about, okay, well, the log odds varies linearly with something, but then it's actually very hard to think about what log odds is. I think regression trees are great for this, very clear. But in general, most nonparametric methods are very black box. So if you think about a random forest, it's the average of like 1,000 regression trees. So it's very hard to kind of pin down, okay, why was this prediction what it was? And people tend to think about things like random forest neural networks as black box methods where you put in the predictors and you get the prediction, and there's not really a lot you can say about what's going on inside. And there's really no coefficients to interpret. I mean, kind of there are, right? Like, so for a regression tree, you have, the split values and you have the leaf values, and that's it. But for something like a support vector machine or something like a neural network, it turns out there are, some parameters in there oftentimes, but there's thousands usually. And so people just throw up their hands and say, hey, what? Like, I can't interpret this. There's nothing there that I can really say why. And that's not true. You can't always say why. It's just like more complicated, okay? But nonetheless, I think this is a feature. This is not a bug. This is a feature, because you should not expect models to reflect the world mechanistically. And if you're looking at a linear regression and you're saying, hey, these 5 numbers, these 5 coefficients are describing the way that the data are generated in the real world, you're completely delusional. And here you are basically saying the real world is complicated. I don't actually believe that this other complicated black box is necessarily a perfect reflection of what's going on in the real world, but a mechanistic understanding of how these predictors lead to this output is not a realistic goal. So it's actually a good thing that these things are not interpretable in this particular way. Now, that said, there are actually many, many model agnostic ways to just like kind of tease into what's in the box. So there's these partial dependence plots. One way to do it, that's on the challenge assignment, Shapley values, Lime. There's a lot of these things. There's a nice, many nice resources. This is one book that's available for free online, Interpretable Machine Learning. And all of these describe, the thing is, you have to remember, all of these describe how the predictions change with the output. So it's one thing to say, okay, when I increase this value a little bit, typically my prediction for my model will increase in this way, or will decrease in this way, or will change in this way. That says nothing about what would happen in the real world if you change this thing. It says nothing about whether you can even change in this thing in the real world without changing other stuff. So you cannot just leap between imagining, that the way the predictions changes is what would happen in the world, or that your model somehow reflects a mechanistic reality. You have to think very carefully about what your assumptions are, like if we're doing causal inference, in order to tie those two things together. And when you're doing causal inference, you have a very specific question. You can think about the very specific assumptions that you need to make instead of in this kind of general descriptive framework where you're trying to say everything about everything. It makes no sense. Now, okay, just because we have these methods doesn't mean that they are a panacea as well. So this is also on the homework. Reading this paper, Mythos of Model Interpretability, which is really about asking about what the hell is it that you mean when you say an interpretable model? Because people just throw this term around, interpretable. I've been throwing it around until now. But there's no one specific meaning to this. You could mean that you want your model to have a causal interpretation, in which case there's certain assumptions that you understand that we need to satisfy. But it could mean that you want your model to be something that you can explain to somebody else without any math. Okay, that's different. You could mean that you want your model to make the same kinds of errors as a human would make, but not make errors if a human isn't going to make errors, so that you can kind of say, oh, I understood why this mistake was made. there's many different ways that you can, and motivations that you can have to define interpretability. And these methods are often not really targeted at any one of those. So you need to actually clarify that idea in your head before you start going and digging around and saying, what do I want this model to be interpretable. What is it that you want? What exactly is it that you want? What do you mean by interpretability? You have to answer that question first. So this is a good place to start.